loosely coupled application, which is a limitation normally for the software. So what we focus with this tool, with Cloudbook, is to solve both problems of parallel and distribution automated code. The first problem is the splitting. Split the source code into a set of small piece of codes that we call deployable units. The second problem is the distribution of the deployable units in the machines in order to start the execution. So for the first problem, some tools needs the programmer create these small pieces. It's not the splitting is not solved. For example, this is the case of a very famous tool, Boink, force programmer to create this piece of code. So it's not solved the first problem. For the distribution, some tools allows communications between the different piece of codes, deployable units, and a master machine. So they allow master slave or client server communication, but not communication each other between all machines involved in the execution. So this work presents a new tool that is able to solve the problem of splitting and also the problem of distribution. So the core of this tool is the creation of a matrix based on the graph analysis of the source code. So if, for example, in this simple program, we have 4 functions, we detect that some functions invoke other ones a lot of times. So this number, when it's very high, imply that if we join function, for example, in this case, function B with main in the same deployable unit, we will save communications. So this is more efficient deployable unit if the one created joining these 2 functions. So the Cloudbook tool, what starts is analyze the source code, create this matrix, and based on this matrix, create a set of deployable units that later on is deployed in the different machines belonging to the cycle of execution. So the Cloudbook tool is composed of the maker, which make the splitting, the analysis, the graph analysis of the source code, the procedural part of the source code, analyzing the different functions and invocations, and create the matrix. And based on this matrix, split the source code. So it's the maker is composed of the graph analyzer and also the splitter. So when we have created the deployable units, we deploy them using the deployer into the different machines. And finally, we have the agents. The agents are executing in the different machines and are in charge of execute these deployable units. So this is the architecture of the system. And in order to assist the programming from the point of view of the programmer, we provide a set of pragmas in order to optimize the parallel execution of your program. In fact, it's possible to take an original program, pass this program through Cloudbook, and create a version, distributed and parallel version of the original program. But if you use with some intelligence this set of pragmas, you can get more performance. For example, one of them is a Cloudbook parallel. It's very similar to the same pragmas or functionalities provided by other tools like CUDA and other ones. This pragma create a function that will be deployed in all machines belonging to the cycle of machines. And for example, the Cloudbook sync waits to determination of all parallel functions invoked. So with this set of pragmas, we can create programs, parallel programs, and distributed programs. So regarding the architecture, we have talked about the maker, the deployer, and finally, we have another one component, which is the stats monitor. The stats monitor takes into account during the execution, takes into account which agents are calling other agents and takes statistics in order to improve the matrix, the original matrix, and make possible a remake of the program based on this real data coming from the execution. And the main file of this architecture is the Cloudbook. Cloudbook is a file created by the deployer that match machines with deployable units. So the deployable units are small pieces of code stored in a distributed file system, which is accessible by all agents, by all machines. And the dictionary which match the agents with the deployable units is the Cloudbook file, which is the main file of the system. The system relies on a distributed file system in order to share all the files of the program, also for sending alarms, etc. So this is not necessary to create single points of failure or bottlenecks based on specialized servers, because agents communicate each other, and when there are some alarms or other important information, can be stored in the distributed file system. So Cloudbook relies on this type of solutions. Well, for stats monitor, in order to illustrate how it works, I have this other slide in which in this diagram appear different agents running. Stats are collected by the stats monitor. This stats contains information about which agents invoke another ones, and this stats monitor create a new matrix. The new matrix is an improved version of the theoretical one created by the graph analyzer, and with the new optimized deployable units created by the maker, if we remake the program, we can get more performance. So this is one of the possibilities. The other possibilities that have a Cloudbook is that you can stop and start agents during execution, and the program doesn't stop. Continue running, even if new agents are added to the execution or removed. Regarding the results, Cloudbook is approximately, depending on the problem, is approximately linear, as we can see in this classical problem and body, in which with 4 machines we speed up 4 times, more or less, 4 times the speed of 1 machine. And also for other applications like this application, which is an intrusion detection system, is approximately linear. But in general, the communications among machines reduce performance. So that's my last slide. The conclusion is that we have created a tool that not only make the parallelization, but also split your program into deployable units, deploy the deployable units in the available hardware, and also the limits of the efficiency of this tool is related with the cost of the communications. Main advantages, the automatic splitting, of course, is one of the main advantages. It's generic, not only implements the master-slave communications, any agent can communicate each other. It's valid for distributed and parallel environments because you can use a lot of machines involved in the execution. Allows dynamic redeployment when agents stops or new agents are added. Also based in performance in order to increase the performance when you take the statistics. And not less, last one, but not less important, low required level of knowledge. We know that programmers would face with a new parallel programming tool like, for example, CUDA or Spark or others, requires a very large period of training. But using this tool, everything is very fast, very easy to understand, and you can program distributed and parallel programs from the very beginning. So that's all from Cloudbook. Thank you very much for your attention.
Thank you, Jose Javier. A very, very interesting matter. Now we have Sergio Galvez. Sergio Galvez is un ingeniero en sistemas, lo voy a decir en español, un ingeniero de sistemas y máster en ingeniería de sistemas de informática de la Universidad Industrial de Santander. Es actualmente estudiante de doctorado en ciencias computacionales de la Santander mismo, y es un pupilo de Carlos Jaime Barros y Christoph Garth. Actualmente es investigador y estudiante de supercomputación y cálculo científico y está trabajando en el grupo CAGE, computación avanzada y de gran escala. Entonces, le doy la palabra a Sergio para su intervención.
Muchas gracias. First, in English, right? First, are you all seeing the slides, right?
Sí, sí, correcto.
Okay. Okay, so Denise has already introduced me and I already sent the video, so I will be brief in my presentation. I will try to. We will start with a small introduction, a brief introduction, and then we will discuss each approach in each site, and then a little bit of discussion about both experiences. First, we all know that visualization is very important for scientific discovery, as it allows validation and discussion of results, and also the remote visualization. Remote visualization is very important for large-scale simulations, for concerns about distribution of resources, access to those resources in different parts of the world, and the problems with data movement, and also because it helps collaboration. That's important. In this work, we will discuss two approaches from two sites, HPC in Colombia and Oak Ridge Leadership Computing Facility in the USA, and we will try to show some commonality between the works, even though they are incomparable because of the resources and the scopes of each site. First, we will talk about 101, which is the flagship computing infrastructure at HPC. Was conceived for GPU-based computing, and interaction and visualization was not originally a concern. The access is via SSH, but the idea was to, along the way in the roadmap, to solve that problem. And there comes Yahe. The user challenges that brought about Yahe were users demand visualization tools and also tools to simplify simulation workloads. Also, it's important they want something similar to the tools they use in their workstations. It's something crucial for them. So taking that into account, we have this very broad guidelines. We wanted something with zero install approach. We don't want custom application in the machines as much as possible. We will use VNC and virtual-GL with virtual-GL. Also, we will use no VNC client and singularity containers to isolate all the components. The conceived user interaction was the user starts a script by Slurm, which start the container and all the components, and from that point onwards, the user will only interact via the browser. That was the idea. For the testing, we took into account a use case based on a simulation code for fluid dynamics for the mechanical engineering department. And the functionality they wanted was a way to fine-tune the simulation scenarios, something quick and easy to visually check the results and make the changes required, avoiding the downloading of the results of partial or not conclusive results. We needed two test sets for the tool. In each set, we have measurements of latency, bandwidth, and FPS for client. We try to emulate the connections used by the researchers in their homes. So we have two example network connections for the last segment. And the first test result showed ample disparity between server and client FPS. We attribute that to the connection. So the second test set was conceived to try to elucidate what was happening there. The test sets are not comparable due to unforeseen circumstances. The university improved the network structure, and that in turn improved the performance of the tool. And also each measurement was different, was independent. we could not measure bandwidth and latency at the same time. For instance, we had to try to use equivalent conditions. These are the results for the second test set, the connection results. We obtained something similar to what we were expecting. And also then at the end of the project, we got access to Renata, and that pushed the results to the performance, to the maximum performance of the domestic connections. So, and then the FPS, which was the important part, they show values around what we considered adequate, and also the users in the mechanical engineering department, they consider that results sufficient for them. The second site is the Oak Ridge Leadership Computing Facility, and the tool they develop is called Site. They provide data analysis, visualization expertise as part of the Insight project. Also, they provide access to the machines, even visualization specific infrastructure such as Everest. We all know that these machines are what we would consider state of the art. They find from the interaction with the teams in the Insight program that the scale of the data calls, the scale of the data makes remote visualization necessary, and the type of the amounts of data they need to make moving data from the site, from the Oak Ridge site to their user site, impossible. And also they also find that the users are interested in easy to use tools and interactive performance. That's very important for them. They are not interested only in the infrastructure, but in the usage. The created site, which is is based on a client-server architecture, and the use case that they based their efforts on was simulation or billion scale atomistic simulation for relation evaluation methods. Each time step was around 500 gigabytes, so data movement was very, very, very cumbersome. The functionality they wanted was to reduce or eliminate data transfers altogether to enable exploratory analysis and visualization. And also they find, and the teams didn't want a normal traditional visualization tools because they were cumbersome and difficult to learn. The results, qualitative results, show there are several publications showing site being used successfully, and also in quantitative results we will center this work. We will show the performance of the encoding decoding engine. In general, the team found out that obviously using the NVENC engine of NVIDIA, using the H.264 codec gave better performance, and that using MSA for decoding was also the best performance of the options, of the alternatives. The main parts of the discussion, the important parts, since I'm very short on time, more computer power should amount to more visualization power, and in situ could be a factor for that. Users always will gravitate to means of interaction that are similar to the ones they use in the machines, something common, and more users bring greater expectations about usability. And what we can conclude is each center tackles a different part of visualization according to the resources and their strengths and limitations. The commonality is the importance of the user experience. This is feature board. I will pass this right away and acknowledge, and this is the end of the presentation. I'm sorry I took a little more time than allocated.
No problem. Thank you very much, Sergio, for your presentation. Very, very interesting. Then we have time, at the end we have time for questions. Now I would like to present Santiago Iturriaga. He is from Uruguay. He's a researcher at the Universidad de la República in Uruguay. He has a PhD degree in informatics from la Universidad de la República. And now he is researching mostly in meta-heuristic and non-deterministic methods for solving optimization problems using parallel and distributed computer. Entonces le doy la palabra a Santiago para que empiece su presentación. Santiago, cuando quieras. Santiago, ¿estás ahí? Sorry for the inconvenience. For some reason, I guess Santiago is not connected as it was connected at the beginning, but it's not. So we won't like to lose time. We go on with the next presenter. And so please, Marcelo, are you ready? We're going to present Marcelo Mora. He is graduated in data processing at UNIV University, and his specialization is technology management, information technology management. Currently, he's a student of a master in applied computing in the Universidad de Brasilia in Brazil. He is working in a very wide field of data and is working for federal government in Brazil. So please, Marcelo, go on.
Hi, everyone. First, I would like to thank the opportunity to be here today. Thanks, Dennis, for the presentation. I'm gonna share my screen. Okay, so let's start. I'm here today to present our work and has a title, Performance Analysis of Main Public Cloud Big Data Services Processing Brazilian Government Data. The work has authors, my friend Leonardo Rebouças de Carvalho, my teacher Aletheia Patrícia Favacho de Araújo, and me, Marcelo Mota. Okay, so we started the work comment in its introduction, the challenges of processing and management, analyzing the current volume of data produced by our society, and the concept of the tools that can be used to handle with this kind of problem. Okay, we talk a little about Hadoop. That is a commonly used tool for this type of needs. They have features such as parallel process and distributed file systems. Okay, so we consult the reports of the last Magic Quadrant Gartner reports to select the actual main cloud providers in the world, and we select the Google, Amazon, and Microsoft. Okay. So, in chapter 2, we discussed the operational and costs challenge to maintain infrastructure to process that kind of tasks. So handling with big data in relation to the use of these tools in offered services on cloud providers, right? So the costs to maintain infrastructure and use the services on a cloud computing. So the paper focus in this scenario, it's made a performance evaluation in the 3 Hadoop services in the 3 main providers. In the case of Amazon, the Elastic Map Reduce service. In case of Google, the Dataproc service. In the case of Microsoft, the HG Insight service. Okay. So on chapter 3, we go a little deeper in the aspects of the Hadoop tools. We explain some features like HDFS, the distributed file system, and the parallelism of MapReduce feature that improve a considerable reduction in process time. And we have other features of the Hadoop ecosystem, such as Pig and HBase in the case of data sources. In the next chapter, we explain the Bolsa Familia program. Okay, it's the government program who seeks to minimize the social inequality of Brazilian poor families. So they register the families and give it the ID number for each family, and monthly make the payments to help their families. So generating the mass of data considered potential for this work to the performance and tests. Okay. Before the COVID-19 pandemic, it's the biggest government program in Brazil. Okay. So our methodology, we start, of course, with provisioning the clusters in the 3 providers, looking the most possible equality in the architectures, the cluster architectures. Okay. So after the data load, we proceed with node exporter agent installation. That agent responsible to collect the metrics and each node on each services on the providers. So then we perform 10 executions of 2 workloads, explore the 2 main features of Hadoop's tools. Okay. To collect and analyze this data, we use the monitoring stack with 3 technologies. So this architecture of our monitoring stack is made by node exporting, send the metrics of each node to data source Prometheus. And we have the Grafana in the front end showing us the data consolidated. Okay. So in each provider, we configured a monitoring stack like this to get all the metrics. Okay. We found 2 related works who tried to make a performance evaluation. The first one looks the performance and energy efficiency of big data applications in cloud environments. And the second one, try to compare the performance in a private cloud with a public cloud, considering the features like elasticity and others. Okay, I'm trying to be fast here. So the results, okay. The graphics allow us to observe the behavior of each service and realize in this case the average runtime of the two workloads. The HG inside has a better performance than the others. We have other metrics. So the CPU and memory usage, we consolidate the data collected considering the resource consumption in each node, okay, just to be clear. So we realize in this case, again, HG Insight use more than twice computational resource than the other two services. So in the next one, we consider the metrics about the disk activity per cluster. So in the read disk scenario, the three providers remain very close, right? I'm sorry. In the write scenario, the three providers remain very close, but in the read scenario, we realized the HG Insights did not consume a lot of resource in this case, okay? So finally, in the network task, Google has a higher network consumption, especially between the execution number 2 and number 6, okay? In the other executions, the providers did not show high network activities, even received or transmitted data, okay? So our conclusion, consider that's data, that's metrics. The graphics show us the Microsoft Azure HG Insight services had a better runtime average and the lowest cost, even considering your higher resource consumption, okay? So our calculation for costs of each execution of the two workloads is nearby 30 cents of dollars in the case of Microsoft, 5 to 9 cents in case of Google's, and the most expensive 83 cents in case of Amazon, okay? That's it. I'd like to thank you, and I'm stay available to any questions. Thank you guys a lot.
Thank you, Marcelo, for your very, very interesting conference. And then we'll have time for questions later. Now, sorry for the inconvenience, but now we have Santiago connected. So I will introduce Santiago. Santiago, as I said before, is a researcher at the University de la República in Uruguay. He has a PhD in informatics from the Universidad de la República, and he's working in meta-heuristics and non-deterministic methods for solving optimizations. And now I will let Santiago talk about his work.
Okay, thanks, Dennis, for the introduction, and
Sorry all for the inconvenience. I got here. We've got a storm in Uruguay, and I got disconnected. We had a little blackout. Okay, so I'll be brief, just like the others. I'll be presenting our work, high performance computing simulations of granular media in silos. I'm not the first author of the work, so I'll try to present as better as I can, and well, answer all of your questions. Okay, so let's see if I can. Okay. Okay, our work studies the simulation of charge and discharge flows of granular media stored in silos. These simulations allow to studying the distribution of pressures exerted on the walls of the silos during the process. This is a very important study because, well, when pressures are too high, the silos are at risk of collapsing. Actually, in 2015, here in Uruguay, a silo like this collapsed, and 2 workers died in that incident. So it's a very relevant study. And we used Lights Public, a well-known open source DIN simulation software for simulating the silos. Lights supports parallel and distributed computing. This is very important because these simulations are heavy computationally, but it does not support dynamic workload distribution. This is a problem because for large simulations, workload usually gets unbalanced, and this harms the overall execution time. So in our work, we implemented a domain decomposition algorithm for lights using MPI, well, based on the well-known strategy, the mobile plane strategy proposed by Markauskas. This domain, dynamic domain decomposition strategy groups processes as using a 1D decomposition strategy, where each subdomain of processes shares a coordinate in a given axis. And well, in our implementation, processes define their workload as the number of particles contained in the subdomain assigned to them. So when an imbalance is detected, the mobile plane strategy is applied to rebalance and redefine the subdomains sizes and locations. For our experimental evaluation, we simulated the loading of the particles at the silo, which are inserted at the top of the silo and moved towards the bottom of the silo. And after the silo is fully loaded, we simulated the unloading of the silo, where the particles leave the silo through a hole in the bottom of the structure. We generated instances, realistic instances of 150,000 particles and 450,000 particles. And we evaluated the static workload scenarios, that is the default workload scenarios for lights, and the dynamic workload scenarios we implemented using different number of processes, 8, 16, and 24 processes for the smaller scenarios, and 16 processes for the larger scenarios. Okay, so the results of our evaluation show that we were able to improve the execution time when compared to the static scenarios by around 34 up to 42% in improvement. And when compared to the sequential execution, we were able to improve speed up from around 6 to up to over 11. That is when increasing the number of processors up to 24. This shows an actually good speed up and increase, nearly linear up to 8 processes. However, the deviation from the ideal speed up increases when the number of processes increases too. This is usual behavior of algorithms when doing these kinds of simulations. Okay, so finally, some conclusions on future work. In our article, we studied the charging and discharging processes of granular media in silos. We implemented this dynamic domain decomposition algorithm, and well, the experimental results show an improvement in execution time of up to 42%. This is heavily in work study. We are actually extending the performance evaluation by considering larger scenarios, and we would like to evaluate this dynamic decomposition method with other applications on science, such as astronomical bodies like asteroids, things like that. So, well, thanks for your attention. I tried to be as brief as possible, and this is my email in case of contact, and well, I'll be staying for questions.
Thank you very much. So I would like to thank all the presenters for being stick on the time. And now we have time for questions. So you can write your question in the question and answer icon you have in your Zoom. I will start can we start with Jose Javier? I have a question about your work. Is very, very interesting. If I don't understand, if I understand right, this is a tool to parallelize a code written in Python. There is a limitation for other languages, or in other words, how a designer, a software designer, have to write his code to be compatible with Cloudbook?
Well, Cloudbook is more an idea of transform original programs into small pieces of software and deploy machines. And is more an idea than an implementation. So Cloudbook is an implementation. For the moment, we have started with Python, because Python is a language it's very productive language, is interpreted and very fast to programming. But the same idea, the Cloudbook idea, could be ported to Java, C#, C, and any other language. In fact, we are trying to evolve the Cloudbook concept to involve other languages. For example, C# and Java. And because Cloudbook is more the idea, the analysis, the procedural analysis of the source code, try to split the program into different parts in order to maximize performance when execute in a distributed way. So the same concepts are valid for any other language. Yeah.
Okay, thank you very much. There is another question I guess is for you, is that you mentioned there is an original static partition for the dynamic partition. Is it so?
Well, yes, the initial Cloudbook analysis of the source code create a matrix of invocations. This is an static analysis because it's based on the source code, but sometimes the source code cannot provide you real information. For example, in a loop, the number of iterations normally depends on a variable, and the value of this variable is the number of iterations. So if inside the loop you invoke another function, it's not the same if the iterations are 10 or are 10 millions. So if there is a lot of iterations, then the functions inside the loop should be together with the invoker. So it means that after a dynamic analysis based on real statistics, you can make the program better. You can split better the program because you can choose with a better and real idea of how functions are invoked each other. You can split the program more accurately in order to get more performance. So even you can get 10 times faster program normal with this statistical analysis. Yeah.
Very, very impressive. There is another question for you. Is how Cloudbook compares to Dask, D-A-S-K, or Parcel, P-A-R-C-E-L. Any comparison in mind?
Well, this question I need to. Have you find these terms in the paper of your because
I guess it's talking about some tools similar of yours. If you are planning any comparisons
yeah.
with other tools.
Well, yes, we have comparing this tool with another ones created for create automated parallel code. The advantage of this tool is that it's quite easy to programming because only needs to learn some pragmas and label your program, your original program with these pragmas. So you can keep your original structure of your program, and you only need to add these pragmas. And the second advantage is that you can communicate against each other, because normally with other tools, this possibility is very limited to client server, or when it's not limited to client server, you must create the deployable units. But in Cloudbook, deployable units are automatic because it's automatic code. Takes your original source code and create automatically the deployable units. So the solution for both problems, splitting and distribution, and the low quantity of knowledge required to start programming are the advantages compared with other tools like, for example, Spark or other parallels tool like Pluto, or there are a lot of tools, in fact. But fast, simple, that solves the both problems. Probably Cloudbook is the unique.
Okay, thank you very much, Jose Javier. Now we will go on with the second panelist, Sergio. We have a question for you. I will read the question in Spanish. It's better. ¿Cuál ha sido la adopción de las tecnologías descritas en tu trabajo por parte de los usuarios?
Should I answer it in English or Spanish?
As you like.
Well, the adoption. In case of Yahe in SS3, the original team, the mechanical engineering research team, has used tool, but the project they were developing ended. So at the moment, it's not being actively used by researchers. We are continuing to try to improve it, and also we are trying to lure more users. One of the reasons why we use BMD for the second test set was to try to lure users from the chemical engineering department, also to test another type of problem. But the option was, I mean, what I tried to say is the project that required the tool ended naturally, and we are now trying to make other users to use the tool. And in the case of the site, Benjamin,
Sergio,
exactly.
I can respond the site part. So while doing this study, in particular user study, we found that there are like 3 different kinds of users in OLCF. So there we have big themes, which includes people who knows about computer science, domain scientists, and they for sure are able to figure out how to visualize their data sets. The other kind of users are those small teams where every PhD student has to do their own simulation. They design everything. They design the experiment, they run the experiment, and they analyze their experiment. So you have like 2 or maybe 3 PhD students. Every student is doing their own experiments. So for that kind of users, sometimes they do not have enough expertise to deal with visualization or data analysis itself. They usually, what we found is that sometimes they are using the incorrect tools, but also we also find that the visualizations, the traditional visualizations tool that exist might not be very usable for them because they do not have a computer science background. So for that, this is why we developed Site in order to reach these kind of users. So the thing that I want to emphasize is that Site is a custom tool which was built for specific needs for this kind of users. So what we have here so far is that when we engage with the users and so on, we try to understand their needs. And sometimes if we can provide a solution using traditional tools like PowerView, BND, BSIT, and so on, we do that. We don't need to reinvent the wheel, right? But in specific cases, as the one that was described in Sergio's presentation and also in the paper, in these particular cases, we have the tools and also all the efforts in order to deploy custom solutions.
Thank you very much. I have not a question, but a comment about their work. It's very, very interesting for me for 2 reasons. One is that now with the current situation, we are not allowed to getting together to analyze data. So this kind of tools for visualization of data in remotely, let's say, is very, very useful. And personally, I'm working in the astroparticle detection is a very specialized field, and we made a lot of simulations about how the cosmic rays reach the Earth and reach detectors. So the first thing we do is a lot of simulations about how this particle behaves and how the detector behaves. And for my personal point of view, for example, I can't deal with the raw data that the simulations spit out from HPC. So for me, it's going to be very, very useful to have a tool like this. So I guess I will contact you later to talk about this.
Okay.
Okay, there is no more questions for you. So thank you very much. I will question for Santiago. If you have questions for Santiago, you can use the chat or the question and answer tool. I have a question for Santiago, but I guess at the end of your presentation you answer, but I would like to explain a little bit more. Your work is very specialized because you are using doing a simulation of the granular media in silos, but you mentioned that these methods and tools you are developing may be used in other fields. Can you talk about this a little bit? Thank you.
Well, yes, actually, I mentioned a little bit this same kind of simulations using granular media are applied to simulations like astronomical bodies like asteroids, which are a conglomerate of little rocks floating in space, and to analyze the collisions of these asteroids. Simulations like the ones we presented in silos are performed using these same tools, like lights and
Okay, thank you very much. We are almost running out of time, but we have a last question from Marcelo. The work Marcelo does is very interesting because we are talking about the non-structured data. How difficult is to find the let's say the primary information? How do you in your perspective did this the government help you, or you have to struggle trying to find information for yourself?
Actually, the Brazilian government offered this information to the public. They use your open data portal. So all information about financial government money, you know, so it's offered to anyone in this open data website. So we waiting for other data about, I believe now the most worry in all countries of the world is to proceed with analysis of the pandemic data, of the health data. So we are expecting another opportunity to use this data too in another work. So our main intention with this work is to assist the customers and decision makers. So even the providers to improve their services related to Hadoop and big data process.
Okay, last question for Santiago. Regarding the speed of the upload, how is the limit on performance, communication, computations? Please be very, very brief because we are going to cut now. I guess we lost Santiago in the storm, but okay, I'm going to write this question for later. We are running out of time, so again, I will thanks all the panelists, all the participants in this track. If you have some questions, you can write or direct it to the authors or any of the emails of ours of the organizers, so we can route your question to the specific person. Thank you again, and let's continue with the other Carla activities. Thank you very much for your participation. Bye-bye.
Thank you. Thanks. Thank you for all the participants.
Thank you all.
Thank you very much.
Hello?
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 So, yep.
Yes.
Carla, no? Yes.
Carla,
Yes,
is that you?
Yes, yeah, but I can't. Okay, everybody's just listening to me. Okay, no, thank you. Sorry, I didn't. Okay. So welcome to the guest keynote for the HPC track. And I would like to introduce to you Cristiana Bentes. Cristiana Bentes received the bachelor's degrees in mathematics from the Rio de Janeiro State University. She received master's and PhD degrees in system engineering and computer science from the Federal University of Rio de Janeiro. She is currently full professor at the System Engineering and Computer Science Department of the State University of Rio de Janeiro. She worked on a number of research projects, collaborating with research groups in Brazil and France. Much of her recent work has been on exploiting the power of GPUs to accelerate a number of applications. She has published numerous journals and conference papers on these subjects, and she's an active member of her research community, co-organizing different HPC conferences. So yeah, I'm very happy to receive and to have you here, and welcome to the Carla conference. You will have 40 minutes for your presentation, and then we will have 10 minutes to answer questions for the audience. Thank you.
Thank you very much, Carla, for the nice introduction. Good afternoon, all. I'm really honored to be here, sharing with you some of my knowledge and excitement about using GPUs for HPC. So let me share my presentation here. So, wait a minute. Okay, everybody see?
Yes.
Okay. Okay. So in this talk, I will talk about exploiting concurrency in GPUs. Well, something is not working here. Okay. So I will start talking a little bit about history, talking about the current HPC systems era that I call the HPC accelerated era, and how did we get here. Then we'll talk about GPUs, why using GPUs, and some features about its architecture. And then we'll talk about an important feature of modern GPUs, which is concurrent kernel execution. And in this subject, I will show you some important research topics which are improving concurrency opportunities, looking for the order of submission, how do we characterize the kernels to run concurrently, how the kernel interferes in each other's, and we'll start, and then we'll talk a little bit about preemption. But first, I'd like to start with a question. And think 10 years back, would you have predicted that about 10 years ago, many of our top HPC systems would be GPU-based architectures? Well, and here we are. More than half of the top 10 HPC systems are equipped with GPUs. And how did we get here? Doing HPC for many years made me see a lot of changes in the HPC scenario. And we started a long time ago in what I call the HPC Jurassic era. From the 70s to the 90s, HPC was restricted to a small niche. The machines were mostly proprietary hardware, usually mainframes and vector computers. And what happened in the 90s that we changed the HPC era? What happened, what was called the attack of the killer micros. This actually was the title of a supercomputing paper. And this was the illustration of the paper, where the author compared the performance of Cray 1 supercomputer against a number of microcomputers interconnected. And by the title, we can infer that the microcomputers were faster than the Cray 1. And actually, the low cost and scalability of microcomputers changed completely the HPC scenario, and we got into a new era that I call the HPC distributed era, where most of the systems were cluster of compute nodes, where in each node we had general purpose CPUs that after the 2000s start to have multiple cores inside it. And what happened on the end of the past decade that we changed again the HPC scenario? What happened is that the Moore law is slowing down. Probably most of you have been in a presentation talking about the end of Moore's law. And I've been to a lot. And people are saying, are we witnessing the end of transistor era? Are new materials are coming? Actually, we don't know yet. But before getting there, what happened in the HPC scenario is that we changed to what I call the HPC accelerated era. Now, the HPC systems are still cluster of computers, but inside the compute nodes, we have more specialized processing elements that we call accelerators. So let's talk about this era, the exciting era that we are now. The key concept in the HPC accelerated era is specialization. And I have a photo of a bike because actually this is a small video that conveys the idea of specialization. If we try to fix this bike with a general tool, we can, but it will be harder and it will take more time. On the other hand, if we use a specialized tool, we do it faster and we spend less energy doing this. This is the main concept of the current HPC accelerated era. The idea is that the systems are heterogeneous, and we have in a compute node a number of CPUs, general purpose CPUs. The CPUs are still there, but we have now other processing elements with different capacities, and they are good in different types of processing. So, for example, in this figure, we have a compute node with an FPGA, a GPU, a TPU, FPGAs are good for certain algorithms that they are programmed to do it. GPUs for repetitive tasks with a lot of data. TPU for neural networks. So the idea is that the CPU offload the computation that are better executed in each processing element, so that this computation will run fast and spend less energy. So for example, if we have FPGA, which is programmed for cryptography, then all the cryptography in your algorithm goes to the FPGA. GPU can do image processing, neural network, TPU do the neural network. So this is the main idea of the current HPC systems, that what we have inside the systems. And the industry is heavily investing in this concept. We have Microsoft investing in FPGAs. Intel is about to launch his own GPU. Google built TPU some years ago for artificial intelligence. Even Amazon is investing in its own chip for cloud computing. And the main question here for this presentation is why GPUs? And well, compared to CPUs, GPUs have a higher level of parallelism and higher memory bandwidth. Modern GPUs have thousands of cores compared to dozens of cores of a CPU. But on the other hand, what's important for this presentation is that GPU does not have an operating system, and it has a restricted execution mode. However, on the tasks that the GPU excels, like deep learning, neural networks, which are highly parallel tasks, GPU does it very well. These are results from NVIDIA comparing deep learning application with running on a CPU. It can be up to 50 times faster running on the GPU. I also want to show you some results about energy consumption, which is also important. Here we have some data comparing Intel Skylake with NVIDIA V100 GPU. We can see that the GPU provides more flops, but spends more energy. But when we look at the rate between flops per watt, we see that the GPU is twice better on this rate than the CPU. Well, we find on the internet a great number of applications that can be accelerated by GPUs from 10 to 100 and more than 100 times faster using GPUs. And NVIDIA announced last semester how GPU is helping in the fight against COVID-19. They have results in sequencing the virus genome. Oxford did in 7 hours using GPUs. They have real-time infection rate analysis. They could screen 1 billion drug compounds in 1 day rather than 1 year. A GPU was the one who allowed the first 3D structure of the virus spike. GPU is also using GPU for using artificial intelligence in classification lung images, in a robot for medical supply, or even in analyzing human body temperature. Okay, now let's take a look inside the GPU. I have a general figure here about the architecture of a GPU. I'm not getting into details of GPU architecture here. I'm just wanted to show things that are important for this talk. And it's important to notice that I will use NVIDIA terminology in this talk, okay? NVIDIA are the most popular GPUs. So a GPU is composed by a number of streaming multiprocessors. Each streaming multiprocessor has his own control unit, his shared memory, and a number of cores. And all the streaming multiprocessors have access to a main memory. What's important for us here is that the GPU architecture is compartmentalized, which means that one SM cannot share the resources of another SM. The only thing they share is the main memory. And about the execution model in the GPU, the piece of code that is offloaded to run on GPU is called a kernel. And a kernel is composed by a great number of threads. Actually, in the GPU programming model, we have to have much more threads than the number of cores of the GPU to hide latencies. But since the architecture is compartmentalized, the software needs to be compartmentalized too. So the programmer needs to divide that great number of threads into blocks so that the hardware knows how he can assign blocks to SMs. One block can run in one SM. One block cannot use two SMs to run. And the blocks does not share resources among the SMs. They just share the main memory. Well, along the years, the GPU hardware resources is growing considerably, taking advantage of Moore's law. We can see here the schemes of some NVIDIA architectures from 2014 to 2017. We can see clearly that the Volta architecture has a greater number of cores. The cores is the small green squares and a greater number of SMs. But the question is, can one kernel fully utilize all these resources? I have a result here from a paper from 2013 that shows the resource utilizations of the GPU on the parboil kernels. Parboil is a famous GPU benchmark, and we have a number of kernels here on this table. And the last four columns shows the percentage of using some of the GPU resources. The first one shows the percentage of the maximum number of threads. The second, the percentage of the registers. The third, the percentage of shared memory. And the fourth, the percentage of the maximum number of blocks. I marked in yellow the resources that use less than 30%. But if we look at the numbers, we can see clearly that this GPU is underutilized. And we are talking about a GPU from actually 2010, because these experiments was run on a Fermi architecture, which is much, much smaller than the architecture that I showed you in the previous slides, than Volta or even Maxwell. So someone can argue, okay, I use less resources, I underutilize the GPU, but I spend less energy doing that. And actually, in the GPU, this is not true. GPUs are not energy proportional. The power consumption does not reduce linearly with the load reduction. So one of the main messages that I want to convey here to you is that it's highly inefficient to underutilize the GPU. And for this reason, NVIDIA GPU provided in the Kepler architecture in 2012 concurrent kernel execution, which means that they allow more than one kernel to run at the same time on the GPU. This technology they called hyperqueue technology. This is an example of a heating map running only one kernel and the resource underutilized, as we saw on that results, and other papers show similar results of GPU underutilization. And if we put more kernels to run, then we improve the resource utilization. And not only the resource utilization is improved, but also the system throughput. We have an example here where we run 4 kernels. On the top figure, the kernels are run one kernel at a time without concurrent execution. And on the y-axis, we see the resource utilization of the kernels. On the bottom figure, we run them concurrently as we can. So kernel 1 runs at the same time as kernel 2. There's no more space for kernel 3 to run. Then kernel 3 runs at the same time as kernel 4. We can see clearly that the resources are better utilized, but we see that the average turnaround time is smaller, and we are improving the system throughput with concurrent execution. But there's a problem in co-scheduling GPUs, and mostly because GPUs do not have an operating system. as we have in CPUs. So in CPUs, we can configure the scheduling of threads to the cores. We can put affinity to run one thread on a specific core or other policies. And a lot have been studied in scheduling to the CPU. On the GPU, the scheduling is performed by the hardware. And on NVIDIA hardware, they do not disclose the scheduling policy. What happened is that the researchers try to disclose this policy doing experiments. And what the researchers call the NVIDIA policy is the leftover scheduling policy that I will explain with an example. Well, suppose we have this GPU and two kernels that will be co-scheduled on this GPU. On the leftover policy that NVIDIA uses, it decides that the first kernel to be submitted get all the resources it needs, and then if there are leftover resources, then the other kernel can use resources also. So what happened here is that the hardware will schedule each block of kernel 1 to 1 SM, and then in this case there are leftover resources, then the scheduler can schedule the blocks of kernel 2 to run on the GPU at the same time as kernel 1. The problem of this policy is that we are giving priority to the first kernel. The first kernel gets all the resources it needs, and the other kernels will run depending on how much hungry the first kernel is for resources. And this priority lead us to a problem that the order of that you submit the kernels to run at the same time matters for the system throughput. Let me give you an example here. Are you seeing the table? I don't know well, I cannot. Can you see?
Yes, we can see. We can see it.
Here, I cannot see the right part of my slide. I have on the right side 4 kernels and how much they use the GPU resources. Actually, this is a very simplification of what happens because we are doing like one number of resource usage for all the GPU. In practice, it's not like this. We consider each resource separately when we are about to run concurrently. But this is just a didactic example. Let's keep it like this. So we have how they use the resources on the right. And on the top figure, the kernels were submitted in the order 1, 2, 3, and 4. So by the leftover policy, kernel 1 gets all the resources it needs. There are leftover resources. We can run kernel 2 at the same time as kernel 1. Kernel 3, however, cannot run at the same time because there's no leftover resources. So when kernel 2 finishes, kernel 3 starts, run at the same time as kernel 1. But when kernel 1 finishes, we cannot start kernel 4 at the same time as kernel 3 because there is no resources for that. On the bottom figure, we see what happens if the submission order was 4, 1, 3, 2. So kernel 4 is the first to be scheduled. It gets all the resources. There is leftover resources for kernel 1. Kernel 4 runs at the same time as kernel 1. When kernel 4 finishes, kernel 3 starts. And when kernel 1 finishes, kernel 2 starts at the same time as kernel 3. We can see clearly in these figures that the second submission order provides better resource utilization and also improve the throughput of the system. So, co-scheduling naively or blindly, if you just send the kernels blindly to the GPU, it may result in almost no performance improvement in exploiting concurrent kernel execution. Mainly because the performance depends on how the kernel requires the resources. So what I'd like to talk now is the main research topics in this subject of concurrent kernel execution on GPUs. And I'll start talking about improving concurrency opportunities. one of the first studies in trying to improve concurrency opportunities proposed spatial multitasking. The idea was to avoid the leftover kernel prioritization and to split the streaming multiprocessor into groups. Each group of SMs or streaming multiprocessor runs a different kernel. It's a simple idea. It's just splitting the GPU into smaller GPUs, and each smaller GPU will run one kernel. But even this, they provide very good results and some speedups of splitting the GPU like this. This was a paper from 2012, the same year that the concurrent kernel execution was launched. And they proposed different heuristics to do the splitting. And they got performance gains for all the heuristics they proposed. So splitting was better than simply put the kernels in any order and submit them to run concurrently on the GPU. The problem is that this technique does not address the underutilization within the SM. And another problem is that this technique would require changes in the GPU hardware to change the way the hardware schedule the kernels to the GPU. Another interesting study is in changing block granularity. As we saw, the hardware maps the blocks of the kernels to the SMs in a round-robin fashion, each block to a different SM at each time. But what happens is that sometimes resources can be available in smaller chunks. Let me give an example of what I'm talking about. Suppose we have this very small GPU with 3 SMs only, and we co-scheduled kernel 1 and kernel 2. Then by the leftover policy, first we give all the resources to kernel 1, and then the blocks of kernel 1 are submitted each to one SM. But suppose there are leftover resources inside the SM, and this can happen. And these leftover resources, however, cannot be used by the huge blocks of kernel 2. The blocks of kernel 2 are too big to exploit these leftover resources. So what the researchers proposed was a technique called kernel slicing, is to reduce the block granularity in order to allow this smaller block to take advantage of the leftover resources on the SM. And they got nice results also. This was a very good paper from 2013. The technique they proposed was called kernel-led, and they got a lot of reduction in the execution time, changing the block granularity. There are other researches that provide changing block granularity too. But the problem is that not all applications you can change the block granularity. In some applications, it's very easy. The granularity of the block, it's a parameter that you can change the parameter. But in some applications, mainly when you are fully exploiting the shared memory inside the SM, it's very difficult to change the block granularity. Sometimes you have to change all the application code. And that's a problem of kernel slicing. Well, the second research topic that I want to talk today is dealing with the submission order. I told you that the submission order matters for the system throughput, for improving resource utilization. And then in this matter, we have a study that uses an optimization strategy to determine the best order to submit the kernels. We model the problem as a series of next step problem. Just to remind, the next step problem is how we can put a number of items inside a next step, considering that each item has a value and a weight. and we want to maximize the profit in the next set without exceeding its capacity. So in transforming this to our problem of GPU scheduling, we consider that the capacity of the next step is the number of resources that the GPU has, the amount of resources, and the items are kernels. So what we did, if we want to submit 6 kernels to run at the same time to the GPU, we assign a weight and a value to the kernels. The weight is proportional to the amount of resources that the kernel requires, and the value is inversely proportional to the execution time of the kernel. We want to give priority to smaller kernels, as we do in CPU scheduling normally. So we run the knapsack to see which are the kernels that provide the best profit, which is the best value, without exceeding the GPU capacity. And as we choose the kernels to put inside the knapsack, we are choosing also the submission order that we should do to improve resource utilization and improve the system throughput. And we got nice results with this study. On the left, we have the results for the average turnaround time. We see great with the dynamic is the name of what we call our strategy, because we use dynamic programming to solve the knapsack. And we see great reductions in the turnaround time, and consequently on the right, we see the system throughput. We see a lot of improvement in the system throughput. So again, as I told you before, just putting the kernel to run blindly, naively, you can lose a lot of the performance that you can get if you co-schedule the kernels with more techniques to understand how they will take advantage of all the GPU resources. The third research topic that I want to talk about is which kernels are most appropriate to be launched concurrently. In this matter, we didn't want to go very simplistic, like, well, let's divide the kernels in memory intensive, compute intensive, and then run together memory intensive with compute intensive. Because this is simplistic, because this GPU has a lot of resources that are used in different ways. So what we did a study to characterize the kernels in terms of resource requirements. The idea is to analyze the individual behavior of the kernels in terms of that resource usage. We use kernel profiling. Actually, we use the NVIDIA tool NVProof. Our focus is to guide the decisions on more efficient concurrent execution, trying to avoid the simplistic, like compute intensive with memory intensive kernel, put them together. So what we want is to pick up a great number of kernels. We pick up kernels from Parboil, Shock, and Rodinia GPU benchmarks. We pick up all the kernels, and we want to classify them in terms of resource usage. Can we create category of kernels to see how they go together in the concurrent execution? So in this study, we studied the following resource requirements: arithmetic operation, how they use integer, floating point, single and double precision, SM efficiency, GPU occupancy, and memory operations, global memory and shared memory operations. And we had around 170 kernels to analyze. It was really hard to analyze the similarity in the use of resources. So we used principal component analysis to reduce the dimensionality of the problem. And then we use a clustering algorithm to create the groups. And these are our results. Of course, I'm not getting into details of the PCA results. What we found 4 different groups in terms of kernels from these 3 benchmarks. Group 1 was the group we call the small kernels. Very small kernels, they use only a few resources of the GPU, and we may think, okay, these are the kernels that will run well together when we test concurrent kernel execution. The problem is that they were so fast that the time it takes to submit the second kernel, they already finished. So they were not good in our concurrency study. The second group was formed by the kernels that were hungry for resources. They were arithmetic intensive and they use a lot of GPU resources to run. The third group was we called medium-sized kernels. They were similar to the second group, but they use less resources than the second group. And the fourth group was the group that provide low occupancy of the GPU. And what we want to know is, of course, the effects of co-scheduling these kernels. The kernels from different groups, how is the effect of co-scheduling them? So we executed concurrently a sample of pairs of kernels from different groups. These are just examples of some of our results. We see these tables, we see some kernels from group 4 running with group 2, then group 3 running with group 2, then group 4 running with group, I don't know because I don't see here the end of my slides, probably group 3. And these numbers that are there is what I call concurrency effect. There is the rate between the time they run alone with the time they run concurrently. And this is a metric where the lower is better. And we found very big concurrency effect in when we put some kernels to run together. This one that I mark means that they would run better one after the other than if we put them to run concurrently. It means that the interference that they generate is very high. And by this study, we could conclude that kernels with heavy requirements on only one resource may prevent concurrent execution at all. If they are scheduled first, the other kernels cannot run with it. And synchronization and global memory access. If one kernel synchronize or have to wait for global memory, the other kernel dominates the GPU, and the kernel that needs synchronization and global memory access in a waiting time would present a higher slowdown. But the most important thing about this study is that we have inconclusive results, which means we didn't find a rule to say, okay, let's run kernels with this feature together with kernels of that feature, they will run good together. Because we found very interesting things in running together in the GPU, like if we put kernel 1 to run together with kernel 2, then we have, well, a nice concurrent effect. They run faster if they run together than if they run one after the other. But using the same kernels, if we put in an inverse order, kernel 2, then kernel 1, they present a huge slowdown. It is really hard to get a general rule on which kind of kernels will run better if they run concurrently on the GPU. So based on these inconclusive results, we try to study how one kernel interferes in the execution of other kernels. And we had a study on kernel interference. Due to that conclusion that resource requirements relations are tricky. So what we did, we used machine learning techniques to try to model and predict if the kernels will run concurrently, and if they run concurrently, if they will interfere in each other. And we selected 60 kernels from our 170, because 170, the number of permutations will explode. We selected 15 kernels for each of that groups from the previous study and executed all possible 3,600 permutations. In this study, we selected different resources to analyze. We analyzed blocks per grid, threads per block, number of registers, and shared memory. And we decided to use these resources because this we can expose before the execution. The programmer knows these resources without having to run the kernel first and then acquire the resource. And we got good results in terms of prediction. These are the curves for the 4 machine learning techniques. The best one on both prediction was XGBoost. And XGBoost provide around 80% of accuracy of predicting if the kernels will run concurrently. And on the interference, we did like a classification. We want to know if 2 kernels run together, if they will provide better execution time running together than alone, if they won't matter if you run alone or not, or if they provide slowdown, if they run together compared with if they run alone. So in this classification, we had around 70% of accuracy in the machine learning results. And what was interesting about these machine learning results is that we can extract the features that matters most for the prediction. And for predicting if 2 kernels will run concurrently, we have the results. There's 2 results here, one for the Pascal architecture P100 and the other for the Turing architecture RTX 2080. We saw that the number of blocks per grids for both kernels are the most important feature to decide if they will run concurrently. And the second most important features is the number of registers of the second kernel. This is because the first kernel enters, pick up all the resources it needs. So the second kernel will run if there are available registers for it to run. And in terms of interference, we have different results for the 2 GPUs. Blocks per grid still the most important feature to see if one kernel will interfere in the other. But the second most important feature for the P100 was the number of registers of the second kernel. And for the Turing architecture, which has the same number of registers as the P100, which means it has a lot of registers, but less resources, less SMs, and less cores. So the number of threads per block was more important to decide about the interference of the kernels. Well, let me see. I am almost finishing, Carla. I will go very fast on preemption. The last topics dealing with preemption. Modern GPUs provide Hadoop preemption. We have preemption at thread level, where we have to wait for the threads to finish, and then we can preempt. In this case, the context to be saved is very small and very fast to do this context saving. But we also have fine-grained preemption instruction level. In this case, the number of resources to save is very high. Modern GPUs have 32,000 registers to be saved. So the overhead of context saving is very high. And in this, also, it's important to do preemption to improve responsiveness, right? As we saw in these figures, if the kernels arrive and the big kernel is running, they will only start execution when the big kernel finishes. So if we have preemption, if we preempt this big kernel, the other kernels can run and we have more responsiveness in the GPU. And in this topic, we also have a research that we propose a linear programming algorithm to provide the optimal preemptive scheduling solution, co-scheduling solution to minimize the make span. However, this solution didn't provide the minimum number of preemption. It just provides, you can preempt everywhere to provide the minimum make span. But as we know, if we preempt at instruction level, it's very, very expensive to preempt on the GPU. So what we did was to provide another algorithm that we called Caterpillar. that try to reduce the number of preemptions on the optimal solution provided by linear program. I don't have time to explain the algorithm. Let's go for the results. We have good results. The red, blue, and green curves are our algorithm running, and the purple curve is the state of art without preemption. What we saw is that the concurrent execution provides 30 to, I don't see the numbers here, 30 to something, 20 to 30 reduction in the execution of the kernels, and the preemption provides further improvements in reducing the turnaround time of the kernels. If we can preempt, we can reduce the average turnaround of the kernels. What was interesting is that we assume a very high preemptive cost. On the blue curve, we assume that the preemption costs 20% of the kernel execution, and on the green curve, we assume that preemption takes 50% of the kernel execution. And even so, we got reductions in the turnaround time with this high overhead of preemption. So concluding, we are in a new era of heterogeneous architecture, the HPC. We are in the HPC accelerated era. We don't know where we are going, although there are many speculations, we don't know where we are going. The current artificial intelligence Big Bang, in this Big Bang, GPUs play a fundamental role. Actually, in my opinion, GPUs were the hardware that allow neural network to come back and to be deep. But exploit GPU to the fullest, we require to exploit concurrent kernel execution, and the hardware support for that is still rudimentary, and co-scheduling is still challenging in the GPU. We studied this in the CPU for many years, and in my opinion, we need to study that for the GPU also. And if we think that now GPUs are on the cloud, they are virtualized, so we are going to create more and more competition scenarios for using the GPU, and probably preemption will be very much necessary in these scenarios. So thank you very much. Thank you, Carla, and all the organization for the invitation, and I'm available to questions.
Okay, thank you for such a very nice presentation. And I have a question here from Guinness Guerrero. He would like to know about the top 500 list on the use of GPUs. He's asking if you think that the supercomputer in the top of the list use all their GPUs most of the time, or invest in GPUs for ranking purposes. And that is why they are in the first position.
Okay, nice. Yeah, this is interesting. People saying that being the top 500 or top 1 is such an important marketing feature that they invest. If I understand the question, is that right? They are investing highly in being top 1 rather than providing good accelerations for their computations. I forget the name, Guinea. I don't think they put GPUs only for being top 1, because it's very expensive to deploy a machine like this. And GPUs are providing acceleration for a great number of applications. So if I understand the question, I don't think so. I think they did this to provide a very efficient HPC system to be used by their applications, and that's what I think.
Okay, thank you. I have another question from Guinness also. Okay. In an HPC cluster with a resource manager, like Slurm, for instance, do you have any advice to optimize the use of GPUs with different users launching different tasks?
Yeah, the advice is quite difficult, but what you do if you want to submit kernels from different applications to the same GPU, then you have to use a framework to do that, because you cannot do it automatically. And NVIDIA provide the MPS framework so that you can submit kernels from different applications. But if you are running on your application and you want to, you know that you have kernels that are completely independent and you want to exploit concurrent execution, then you have to assign each kernel to a different stream. GPU has streams for you to do that. So you assign to different streams. But to have an answer, will they run well together or not? This is really tricky. You know, it's just what we are studying a lot, and this is not easy to answer right now. I think you have to do experiments to try.
I have another question about Álvaro Fazenda. Congratulations for the presentation. Could you please talk a little bit about the computational cost for the development method to change the task allocation for concurrent kernels? It can be used iteratively in case of possible dynamic imbalance.
I don't know if I understand the details of this question. Actually, the only thing you can do in your application to exploit concurrency is what I told you, put in different streams. Then you submit it to the GPU and the driver will get, well, you are in stream 1, you are in stream 2, I can put the run at the same time. But load balancing inside the GPU, no, there is no load balancing inside the GPU. What you can do if you want, if you know very well your kernels and you want to do load balancing, you have to deal with the streams, right? You know that at the kernel 1 run well with kernel 2, so you put on the stream 1 and stream 2. And kernel 3, they don't run that well. Put on stream 3 because they submit the kernels in the order of the streams, right? But this dynamic load balancing, no, they don't have it in GPUs. This is a very interesting research topic.
Yes, we have more questions. We have a question from Robinson Rivas. Do you believe there is a technological space for a future substitution of GPUs, for instance, with specific mini processors made specifically for neural networks calculations or another specific purposes?
Yeah, this is a good question. Actually, it's difficult for me to say, but from the principle of specialization, you are right? If you follow this avenue, the idea is to have more and more specialized processors, and Google invested in the TPU. Rather than producing a new GPU, Google invested in a processor specific for AI computation. And GPU had to go after and include tensor cores inside the GPU so they can run better AI. So I am not a visionary in this area, but I would say maybe yes, we will be more specialized in the future. I would say that.
Okay, so we have more questions. One more question, the last one. From Carlos Barrios, for your opinion, what is the real future of the GPUs against the TPUs on the post-Moore architecture? Post-Moore architecture.
Yeah, good question. I think GPU is running after GPUs with the tensor cores. They want to compete with the TPU in terms of a good processor for AI. If you see NVIDIA's presentations, they are now, we are AI. AI is the main topic they are talking now. So I think there's a run for the two, and we don't know what the industry is coming with new technology, but GPU is getting specialized in AI also. So I don't know, maybe we see in the future a GPU for image processing, just like this GPU that we know, and a GPU specialized for AI. with more tensor cores and more tensor processing. That's what that's my idea. I like those future questions. It's so nice to have those discussion. It's a shame that it's not presential and we cannot talk and discuss, because I like this very much.
Okay, yes, that's correct. So I already are running out of time. So I would like to thank you one more time for such a nice presentation in the name of the conference. Thank you very much.
Thank you, Carla. Nice to see you again. It's a shame that we are not together in Ecuador right now. But
yes, that's too bad.
Yeah.
That's too bad, yes.
At least we are conveying our message and people are participating. That's very nice. Thank you very much for the invitation.
Thank you. Thank you very much.
So
I think the next, I think Claudio needs to.
Okay.
Yes, I think.
Okay.
Right?
Yes, it's done.
Session.
Thank you very much. Yes.
Okay, so I will go.
Hi, how are you?
Thank you.
Okay. So good afternoon, everybody. We're almost starting the next session. It's the second session in high performance computing. We're just waiting a moment to confirm that the panelists are all connected, which I see Juan Fabian. Is Danilo around?
Is here.
Danilo?
No, Fabian.
Fabian. And Luis Alejandro Torres? So maybe we could, so we don't waste our time, if you agree, Juan Fabian, maybe we could start with you.
Okay.
All right.
Share my...
Danilo.
Hello.
Now, Danilo, are you there?
Yes, I am. Can you hear me?
Oh, perfect. Excellent.
Oh, nice. Awesome.
Okay, so we're going to start. Thank you, Fabian. We're going to start our second high performance computing session.
Okay.
We will have 3 talks, and after these talks, we will have a question and answer time. But please post your questions during the talks in the question and answer icon, Q&A, at the bottom of the screen. So we would have a collection of questions, and we'll go in order with each of the presentations so you could, so we could ask the questions. So our first talk is accelerating machine learning algorithms with TensorFlow using thread mapping policies. The speaker is Danilo Carrastan Santos. He's a double degree PhD in computer science by the Federal University of ABC, Brazil, and by the University of Grenoble, France. He is currently a postdoctoral researcher in Parallel and Distributed Processing Group of the Federal University of Rio Grande do Sul, Brazil. So it's a pleasure for me to leave you with Danilo.
Thank you. Hello. Thank you for the opportunity to present our work. And actually, this work was mainly performed by one of our undergraduate students, Matheus Camargo, and our task was mainly to provide him support during his studies. And now I'm going to present a short summary of the work that he performed during his studies. And the goal of his this study was to see to study about the performance, the CPU performance of parallel multi-threaded machine learning algorithms that developed under the TensorFlow machine learning library. And when it comes to multi-threading, an important question is how different mappings of CPUs, threads to CPU cores impact the performance of the algorithms. And this problem is known in the literature as the thread mapping problem. And in fact, there are many works in the literature that explore these thread mapping problems. And they work more on traditional HPC applications. And here in this work, we want to perform the same approach to explore different thread mappings, but take into account a CPU parallel multi-threaded machine learning algorithms built on top of TensorFlow. And here, just to clarify a little bit about the idea of thread mappings, here we have 3 examples of thread mapping policies, which dictate the logic of the assignment of threads to cores. So we have 3 examples here, and the scatter, the compact, and the round robin thread mapping policies, which are as well the policies that we used during the experiments. And as you can see here in this picture, different policies has a different logic behind the assignment, and we can expect different interactions with the hardware. So with the logic of the application as well playing a factor, we can expect with different thread mappings, we can expect different relationships, different behaviors with the hardware, and consequently different performances. And well, in regards to machine learning and CPU parallel machine learning with TensorFlow, we used a benchmark called AI benchmark, which contains many machine learning recent machine learning algorithms and models, and so it enables as well that we use CPU with that as well. Sorry, if that as well was implemented using TensorFlow, and also enables the CPU execution of these algorithms. And for the experimental evaluation, what we did was very simple. Actually, we took this benchmark and we executed this benchmark, taking into account different thread mapping policies, and notably the 3 ones that I mentioned earlier. And here for the results, we have this first set of results, and we separated the experiments into 2 phases. The first one is the training phase of the benchmark. And this training phase is the phase that we have the machine learning models and we want to optimize them for their task. And in this graph, we have in the x-axis we have the many machine learning models that are present in the AI benchmark. And on the y-axis, we have the performance improvement of a certain thread mapping policy, taking in comparison with the full thread mapping policy of the Linux operating system. And as you can see here in this figure, we in our experiments, we achieved up to 46% performance improvements. And we also noticed that the computer vision tasks here, notably represented by the Inception and the ResNet models, they they consistently benefited from the different thread mappings. And we also noticed that the scatter and compact thread mapping policies, they consistently, in the majority of cases, contributed to a better performance. And in this second set of experiments we measured the performance of the inference phase of the benchmark. And this inference phase is after the models are optimized, we actually use this model to their purpose. And here, similarly, we also achieved interesting performance improvements up to 29%. And we also notice here that scatter and compact also consistently provided performance improvement in the majority of cases, not all of them, but the majority of them. As opposed to round robin, in its turn, that there are many cases that it actually didn't contribute to better performances. And well, to summarize, so we clarified a little bit about what can we expect if we change the thread mapping policies, the thread mappings, when we account the CPU execution of parallel machine learning algorithms using TensorFlow. In our experiments, we achieved interesting performance improvements up to 46% in the training phase and 29% on the inference phase. And these results are interesting in the sense that we only need to change an environment variable to get these improvements. We don't need to buy an accelerator device even though like GPUs, they effectively can increase performance by a lot, but we don't. In this case, we don't need to have an accelerator device to make our applications more faster. We don't need to drastically change the code of the benchmark of our machine learning algorithm to get these performances. We just need to straightforwardly just change a variable in here you go, we have the performance. And well, okay, we looked, we understood a little bit better about what happens when you change the thread mapping, but another, perhaps the more important question is why these things happen. And this is one thing that we want to go for as well. And for this task, we can go there's many ways that can go. But for instance, we can look at hardware counters to see what's happening in the architecture in the processor during execution. And we can also get a better understanding about the machine learning algorithms that are present in the benchmark to see if there's some policy that can benefit to a certain characteristic of these algorithms. And also another interesting question that can be studied is if these thread mapping policies were enabled on mobile devices, for instance, what the effect is that we can obtain. And actually, like we have mobile processors, which are multi-core processors already, and we have machine learning being actually run on these on mobile devices as well. So it'd be interesting to see as well what can we expect when we account mobile devices. And here, just to thank all of our funders to make this work possible. And that concludes my presentation, and I thank you very much.
Thank you very much, Danilo. So as I explained before, we're going to have a question and answer session after the 3 talks. So we'll give now the word to our next speaker, who is Luis Alejandro Torres. Are you there?
Yes.
Perfect. So our second speaker is going to talk about methodology for design and implementation an efficient HPC cluster. Luis Alejandro Torres is a PhD student in computer science at the Universidad Industrial de Santander in Bucaramanga, Colombia, under the supervision of Dr. Carlos Jaime Barrios. He holds a master in system engineering and informatics.
He is the CTO responsible of technology and operation of the Supercomputación y Cálculo Científico SC3, Supercomputer Center at Bucaramanga. So it's a great pleasure to give the word to our next speaker, Luis Alejandro.
Thank you for the introduction. And the topic of this presentation is a methodology for design and implementation of efficient HPC cluster. And And for years, HPC cluster had been deployed through the process of loading source codes and configuring and compiling in order to require to implement the HPC service. In addition, its administrator based on their experience and knowledge and through the series of consideration to design and implement a cluster. This is step by step, and could take considerable time to get the cluster up and running for the users. And to reduce this time, several open source initiatives have emerged, so that ROX, Oscar, or OpenHPC. And respect that ROX and Selenium distribution with all software components for cluster deployment and management. And Oscar is the fully integrated software packet that will be installed after the cluster operating system, and both reduce the complexity of installation and configuration. But the common problem with these tools is the lack of balance between the customization and easy to use. OpenHPC was launched in 2015, and this seeks to integrate best practice in HPC and provide a software repository with the tools needed to deploy an HPC cluster. For this reason, we selected OpenHPC as the basis for our implementation methodology that was tested and won on the cluster of SS3. And methodology, basic architecture, and this is in the first part. We show the general proposal for the organization of items that are considered based on the implementation of the HPC cluster, and how our methodology proposed to have the storage system and IO server to manage sensitive information. In addition, and to high-speed network have been used in InfiniBand for communication and synchronization between nodes, and the fiber optic channel for communication between IO server and the storage system. And the other elements present in the figure are the regular elements and clusters of the master node and the compute nodes. And network configuration. It's necessary to provide access to network, and the first for communication between the master node and the compute nodes, and will be for the exclusive use for resource manager. And the second network will be responsible for data traffic and between the master node, compute nodes, and IO server. And respect compute nodes to provide internet, and we recommend configure the gateway and can be redirected to the IP address to the master node, and keeping in mind that the master node have access to the internet. And this recommendation relies on security policies to isolate compute nodes from the external networks and potential attacks. And the basic system. Previously, we have described a basic organization of the essential elements on HPC cluster and on the simple configuration of the network to obtain acceptable performance. Now, we will show the software elements that are considered essential in the deployment of the efficient cluster. The first of these tools is a network time protocol. The NTP server is on the master node, and that the compute nodes and the IO server be synchronized with it and not against the servers. This next tool is network file system, and this is really responsible for exporting the logical volumes on the different nodes, which is in our case including the user home directory, the directory where the platform software will be stored, and the shared directory for the projects and or reserve groups. And respect the InfiniBand, and OpenHPC comes with support for both Omnipad and InfiniBand. In our case, we have selected InfiniBand because it's the result that is valuable in one, and I do not indicate InfiniBand is better than than on pad. Respect and memory use limits, and Linux has a series of restrictions for the use of resource by the user processes. And a good practice is to establish new rules that allow the execution demanding tasks. These rules include the memory limit and the maximum number of the open files per process. And respect the HPC modules. And the environment modules allow the platform software to be encapsulated by creating a script that contains the necessary environment variables for the execution of the its application. And there are two types to the scripts, one based on TCL and the other based on Lua. It's recommended to use Lua because it allows us to build more detailed scripts. And respect scientific software, it's recommended to install one of the scientific software repositories that come with OpenHPC. In our case, we have used SPAT. PowerShell is a great tool for management multiple nodes, and it's designed to execute commands in parallel, and this tool is highly scalable. Finally, is NHC, and this allows Slur to monitor the status of each of the compute nodes and verify if they are working correctly. Once the base software is started, we must choose which workload manager will be used. There are two options when using the OpenHPC repository, Slur or PBS. And we selected Slur because it's the best node to administrate on a user and the one cluster in special. And workload manager. This is a task that can take some time and may have a certain degree of difficulty depending on the experience of the administrators. According to the Howard observation, it's convenient to install Slur and Muse from the OpenHPC repository and allowing for rapid implementation. And this implementation allows us to spend more time configuring task manager according to the cluster use policies. And we must pay attention to the configuration of the scheduling section and special parameters, the following parameters: the scheduler type, the select type, the select type parameters, and priority type. And the configuration, these parameters, and dependent on his cluster and his police, but the correct configuration but allows better use of resources by the task manager. LDAP. And this topic requires a typical LDAP installation, downloading and the source code, configuring and installing. This method is necessary because in our installation, we use dynamical groups, and this allows us to assign more than one group than each of the users. In addition, we noticed that the LDAP packet that comes with the repository is outdated and many modules are not included. Respect at least the LDAP in the compute nodes and the master node, and we have used SSD to avoid access problems to the platform in case the LDAP server fails completely or if there is no redundant servers. SSD creating cache users of LDAP and the node where is instead installed. Is a crash in LDAP, of course, SSD allows users to continue logging into the platform without any inconvenience. Results and conclusion. And this session, we show the results obtained from SPL benchmark to demonstrate the correct operating of the cluster using the proposed methodology. However, these results are not directly related to the various administrative tools that have been presented in this work, and that cannot be quantitatively evaluated, and our recommendation of the authors based on this experience in the implementation and administration of the HPC labs. Finally, we note that our implementation using the methodology in this work allow us to achieve an efficiency of around 81% in average in HPC in SPL tests. In conclusion, the use of the proposed methodology in the design and implementation of the cluster, relying on the software repository and the best practice recommendation provided by OpenHPC, simplify the task for the HPC laboratory startup. In fact, the decrease in platform update times was also observed along with the complexity and installation and configuration of certain scientific software using SPAC. And finally, according to the result obtained from the HPL test, we were observed that the implementation of the cluster using the described methodology presented good performance results when executing and tasks that require intensive computation. Thank you.
Thank you very much, Luis Alejandro. So I remind you that we'll have questions after our next talk. So now we will pass to Juan Fabian.
Yes.
Perfect.
Here.
So it's a great pleasure to announce the next talk, which is called Estimating the Execution Time of the Coupled Stage in Multiscale Numerical Simulations. The speaker is Juan Fabian, who is a doctoral student at the Laboratorio Nacional de Computación Científica, LNCC, in Petrópolis, Brazil, under the direction of Dr. Antonio Tadeo Gomez. So I leave you with Juan Fabian. Thank you.
Okay, can you see my slides?
Yes.
Okay. Hello everybody. My name is Juan Fabian, and today I present my research work titled Estimating the Execution Time of the Coupled Stage in Multiscale Numerical Simulation. Multiscale phenomena are observed in nature, and the simulation that represent this phenomena must be based on robust methods. One type of this method are the multiscale numerical methods. Computationally, multiscale numerical methods can be seen as a two-stage process. In this work, we use multiscale hybrid mixed finite element method in the experiments. In the synchronous stage, local problems are solved. In the coupled stage, the global problem is solved. The asynchronous stage could be offline. So here we consider only the coupled stage for estimating the execution times. The mesh information is defined, and the numerical parameters L and M. M defines the number of partitions of the edge of the mesh, and L defines the degree of Lagrange polynomial in each such partitions. The execution times in the coupled stage is related to the time to solve the linear system of the global problem. The system is shown here, and his dimension is affected by the numerical parameter L, M, and the mesh. Refining the mesh increases the dimensions of the matrix. Increasing L or M makes the matrix not only bigger, but also denser. Sometimes users of multiscale simulation require to use supercomputers for their simulations, and they don't know how long are their simulations. Well, in the photo we show we show the Santos Dumont supercomputer in Petrópolis, Brazil. Well, thinking about it, in this research, we propose an approach to estimate the execution times. We present Nazca approach. This approach has two steps: the step of learning and of production. We use all simulations. A characterization process is released considering three data space related to numerical method, computational architecture, and performance metrics. In the learning process, we realize feature engineering in the data and define the learning techniques. After that, we obtain the predicted model, which is put in production for estimation the execution times. For new simulations, the characterization process and the feature engineering that we did before, we use here. To view a predictive model, we use a tree-based architecture. Remembering the numerical details of the couple stage, we use the numerical parameters L and M for the building. And in the left, we use linear models. For the selections of the model on the left, we perform an empirical analysis. In this analysis, we really realized 1,000 repetitions, training and testing a specific model. We collect a fifth model and its prediction band for each repetitions, and we analyze two hypotheses. The hypothesis HB0 and HR0. The first is related to the variability of the results, and the second is to the reliability of the model. We consider 5 models as shown in the table. Model 2 and 3 were considered because we use the MAMPS parallel linear solver. The empirical analysis is realized for each combination of L and M. In the following, we analyze 2 representative cases, a successful case, and a successful case. For a successful case, L is 0 and M is 2. And for the other is L equal to 4 and M equal to 8. In this figure, we show the results of 1,000 repetitions for each model. The red and blue line represent the prediction bands, and the green line, the fitted model. In dots, we can see that the data for this combination of L and M. The model 1, 3, and 5, there are points that fall out of the prediction bands. And for that, we refute the hypothesis HR0. And for the hypothesis HV0, we refute in the models 3, 4, and 5. Here, the model 2 is the only one in which we cannot refute both hypotheses. This is in the case L equals 0 and M equal 2. For the other case, we have a similar information in the figure, and we can see that our technique cannot select a proper model using empirical analysis. For that reason, we use by set in open resource, and we select the most straightforward model, the model 1, the model most simple. After the empirical analysis for each combinations of L and M, we select the best model as shown in the table. And also for each combination of L and M, we calculate the squared error in that test data set as shown in the figure. Finally, we compare our technique with 3 well-known regression techniques: model-based tree, Gaussian process regression, and random forest. Nazca gets the smallest error, and we can see the considerations of the numerical parameters in the building of the tree. What's a good choice? As a conclusion, we show a real summary of what we did, And we emphasize that our proposed technique achieves the smallest error of generalizations. There are some future work, but the most important to say is that we can use our approach with other multiscale numerical methods that have two-stage process. Well, would like to thank CAPES, CNPq, FAPERGE, and FINEP for supporting this research. Very thankful.
Thank you very much, Juan Fabian. I also thank the three speakers for such different and interesting talks. And we'll now proceed to the questions and answers. So I propose that we go in order as the presentations were done. So is there any questions for our first speaker about accelerating machine learning algorithms with TensorFlow thread mapping? I have a few questions. So I would like to ask Danilo the following questions. Since the results are hardware dependent, can one expect similar results in other hardware platforms? Under what similarities?
Yeah, I think this is an interesting question because we have because by changing the thread mapping policy, we have different behaviors, interactions with the hardware, and these interactions are defined by how the hardware is developed. So it's, well, we can of course expect differences in performance. I don't expect that we, for instance, we consider another architecture to explore thread mappings into different processing devices. I don't expect that we have the same results as, for instance, getting scatter and compact consistently good results. But my guess is yes, we are going to have different thread mappings will lead to different performances.
This leads to my next question. What will be the expectation of these results in new hardware technologies for exascale and exascale, since hardware is advancing fast for AI applications?
Yeah, I think, well, in this regard, I think we need to, well, we always pursue for better performances, either by increasing hardware, reducing, making processors more powerful, but we also always think about peak performance, always going towards exascale. But reaching exascale is not only a matter of getting better processors and making better interconnections and better supercomputers. We also need to make the applications more faster. And I think in this regard that our work situates, which is ways to make our applications run faster, but as well with low efforts, because thread mapping is quite straightforward to be used.
Thank you. And finally, I have one more question. Is there any heuristic to decide which thread policy mapping to use beforehand? I know it's, you'll say that it's hard to decide on it and you need more clarity of what's going on, but is there kind of an idea of what a heuristic could be?
Yeah, it's a very nice question, actually. Like many of the works that explore thread mapping is the purpose of these works is to actually to broaden our knowledge about what happens if you change the thread mapping, and it is actually being quite challenging to find either an heuristic or either machine learning to make a classification as to which thread mapping policies is appropriate. And well, I don't want to say that's not a problem, because perhaps it's not, but it's nevertheless it's a quite interesting research topic to approach.
Thank you very much. So we'll wait to see if we get some other questions before we leave you later on. So let's pass to Luis Alejandro. Are you there, Luis Alejandro? I don't know if he's with us. Luis Alejandro? Because we have several questions for you. Well, while I wait to see if is Luis Alejandro connected? Okay, so let's see, let's make some questions to our last speaker, who was Juan Fabian. Juan Fabian, are you here?
Yes, I'm here.
Perfect. I'm trying to see if I have here some questions for you.
Okay.
In the meantime, I have a few. So I'm very interested in your talk, since I work in several projects involving multiscale numerical methods, like underwater reservoir flows, oil reservoir, pipeline transportation, etc. So I wanted to know, are there any basic criteria to decide the type of learning technique that is more suitable to be used?
Well, I don't know if I understand the question, but for decide what technique to use, we suppose that linear models maybe can be an option. And then we compare it with other techniques, and we analyze if our supposition was good or not.
So if I understand correctly, you do compare with different techniques?
Yes.
And then decide? Because I had understood that it was...
Initially, we suppose a unique technique, but then we use other techniques to compare it.
Oh, perfect. Okay. Thank you. And I'm still waiting here for a moment. I have another question for you. Can this methodology, I think you mentioned it, be applied to other multiscale numerical methods that have a two-stage process? What should they satisfy, and how great is the effort?
Okay, in the literature, we know that exists two methods that present this two-stage process. We don't use yet that method, but we expected that our approach can be applied to that method. Honestly, we don't analyze more extension yet.
Okay, but you have an idea of the systems of equations that could be put in this context. I mean, because it's very general. You basically say that we need two stages, but does any kind of PDE equation, the normal ones we use in applications,
okay,
suitable to do this, or it has to have very particular conditions?
Well, we suppose that our technique will be general, but now we don't have results. All we know is that possible this technique will be applicable.
Okay.
And mathematically, well, I don't know exactly what kind of mathematics I can say about the method because I only use the multiscale method. but I suppose that other techniques that I know in the literature, two of them can be extendable.
Perfect. Thank you very much, Juan Fabián.
Okay.
So we'll now pass to Luis Alejandro. I think he's now with us. Am I correct?
Yes.
Perfect. So we have several questions for you. The first one asks, how long does it take to put together the HPC configuration you described? This is by Israel Pineda.
Hold on, it's complicated, but in the first step of the implementation, we had to small the nodes of the cluster, clean and other tasks, but put together all tools. We 1 to 2 days, more or less. Yes.
Okay. And there's also some other question. Do you use any system that helps you to compile the scientific applications like EasyBuild or SPAC?
EasyBuild and SPAC is a repository with scientific software, but these tools really do a lot of compiling this software, but this software this automatically, yeah.
Okay. And one more question we have here coming to me is, how have you configured the priority parameters in Slurm, understanding that you have the multi-factor plugin active?
This task is really now it's complicated, but this configuration is there's other game. We change this parameter 2 or 3 times, depending on the cluster configuration, the time to configure these parameters.
Okay, and I have a question for you, if maybe we receive other ones. Meanwhile, is under what circumstances do you recommend shifting to your methodology?
Recommendation, in especially in our case, we use this methodology for because one is a all cluster, and this is allow us implement the cluster and the fast. We recommend that this, in special with the administrators introducing in these topics.
So if I understand correctly, it could be after several upgrades?
Excuse me?
Or that the recommendation could be that after you have several upgrades of your system, instead of going through the one that comes with the computer system, you should try and could implement this open HPC.
I don't understand your question.
You don't understand me? No. So I was asking, under what circumstances can we shift, or you recommend we shift to this methodology? That means I was trying to imagine what would be the scenario that would...
Okay, we recommended this scenario, and especially with the cluster is all cluster, or especially with the administrators new in these topics, and especially the HPC administration.
Okay, so I'm looking to see if I have any other questions. It seems we have gone through the list of questions. So I only want, again, to thank all the panelists, all the speakers for such interesting talks. And I think we have still a few minutes before we go to the next session. So please wait. while it's introduced, and thank everybody. Thank you for being with us, and thanks to the organizers for such a good effort to have us, well, if not together physically, at least sharing all this interesting talks. Thank you.
Agradecemos nuevamente a los panelistas y a los expositores de los tracks presentados. Dando continuidad con el Congreso, me permito presentar un video de parte de nuestro auspiciante ThinkLink en la parte de Marketing de Estudio. A continuación les presentamos a Aaron Sobrik con toda la presentación referente a qué es ThinkLink.
Hello and good afternoon. I hope you're all enjoying the conference so far. Thanks for joining. So today I'll be talking a little bit about the company I work for called Sendio and the Linux-based remote desktop server product that we develop and support, known as ThinLink. So firstly, a little bit about me. My name is Aaron Sowry. I joined Sendio in 2008, initially as a developer, but I am currently working as a technical pre-sales consultant and systems engineer, working with ThinLink to help people get up and running with it, to evaluate it, to set up proof of concept installations, and eventually migrate from the proof of concept to the production stage. Since 2015, I've been based in New Zealand. So the time difference means that when you see this, it will be a pre-recorded presentation, which means I won't be available at the end to take questions and give answers, but I will provide you with some contact details if you need to get in touch. So firstly, a little bit about Sendio. Sendio was founded in 1992 in Linköping in Sweden by several graduates of Linköping University. Some of you might recognize Linköping University for its involvement with NSC, which is Sweden's National Supercomputing Center. Initially, Sendio was providing open source and Linux-based consulting services. You might also note that the initial release of the Linux kernel was made in 1991. So, being formed in 1992, Sendio were very early adopters of this technology and have been working with it ever since. And by some measure, this perhaps makes Sendio one of the oldest Linux-focused companies in the world. Up until the late 90s, Sendio developed a firewall known as Fuego, as well as providing consulting services. But now we are exclusively focused on ThinLink, exclusively focused on developing and supporting the product. And ThinLink is a Linux-based remote desktop server. That's what we do. That's all we do. And these days, Sendio as a company is located in Mjärdevi Science Park, with other companies such as Saab, Ericsson, who are actually also ThinLink customers. So ThinLink itself was initially developed as a consultancy project for one of our customers. But when it was finished, it slowly became more and more popular to the point where we wanted to release it as a supported product, as an officially supported product. And in 2003, we did just that. So in 2003, Sendio made the first official ThinLink release public. And today ThinLink serves many thousands of users all over the world, and that process represents 17 years of testing, research and development, to the point where we now have a very mature, stable and field-tested product. And here we have a list of just a few of our customers. We have customers in all sorts of different sectors all over the world. The selection here is really designed to highlight ThinLink's usage within the, excuse me, within the HPC sector. And you might recognize some names there. Not least of all, Indiana University and MAN, who, if you were present for the morning's sessions, you may have seen give a couple of presentations. But besides HPC, ThinLink is also prominent in other sectors such as manufacturing, telecom, research, healthcare, financial services, VFX, e-commerce, and of course HPC. So ThinLink, as mentioned, is a remote desktop server. It's designed to implement what's called server-based computing, to publish desktops and applications to remote users. It's built on open source components. So for example, the video is transported using the VNC protocol. We use pulse audio for the audio transport. We use cups for printing, and all traffic is tunneled over a secure SSH tunnel. ThinLink uses a fair licensing model. We don't license per individual named user. We don't license per CPU. We license per concurrent user, which means that you only need to have licenses available for the number of users you expect to be using the system at the same time. Even if there's 1,000 potential users, if there's only ever going to be 200 using the system at one time, then you only need 200 licenses. It's a product which is fully supported by those who built it. We don't outsource our support to call centers or to third parties. When we support our product, and the people that you will be communicating with when you need support are those people who built it. They are the developers and employees of Sendio, and we're quite proud of our support. In 2019, we dropped support for Windows desktops and applications. So now we are 100% focused on Linux. That was a conscious decision. We want to focus on our core customers, and our core customers use Linux. This does not mean that you can't use ThinLink to access Windows desktops and applications. It just means that that functionality isn't included out of the box. And if you do need assistance with accessing Windows desktops and applications along with Linux ones, then we can provide assistance around that. ThinLink has support for all major distributions and desktop environments. So whatever your preferences are around using Linux, they're likely to be supported under ThinLink. And these are just a number of different examples of distributions that people are using with ThinLink, and a couple of examples of the different desktop environments that people are using too. We generally find that in terms of desktop environments, it's the more lightweight ones which are more appropriate for remote desktop environments which need to support a large number of users. So desktop environments such as XFCE or Mate are quite good options here. Your choice of distribution really doesn't matter, it's just whatever suits you and your particular application, but all the ones shown here are more or less fully supported. On the client side, ThinLink has clients available for all major platforms, so that's Windows, Linux, and Mac. Plus, we also provide an HTML5 client which can be run in the browser, and because it's HTML5 based, that means that there is nothing to download. The HTML5 client or the browser client does not have feature parity with the native clients, so there will be some features missing, but for many people it's actually good enough to use as a daily driver. We also have clients available for thin client devices, such as those provided by iGel, HP, Dell, Wise. And we even have an ARM client which can be used on certain pieces of ARM hardware as well. Security and performance are key focus areas for ThinLink. We do tunnel all traffic between the client and the server over a secure SSH tunnel, and that means that ThinLink can be used safely over unsecured networks such as the internet, which allows people to be able to access these resources from home, over the internet or over 4G, wherever they are. Performance also plays a part in this because ThinLink is specifically optimized for high latency and low bandwidth connections. This means that it performs well over cellular networks and perhaps internet connections which are not high quality as well. We support full duplex audio, which means microphone support as well as speaker support. We support things like printing, local files, multiple monitors. ThinLink also supports multiple authentication mechanisms, including smart cards. On the server side, we have load balancing and redundancy built in. So ThinLink will normally be configured as a cluster rather than a single server, and that means that as people log in, ThinLink will distribute the sessions over the servers in a cluster in order to spread those resources and make efficient use of them. ThinLink is built on Unix principles, and that means that anybody who's familiar with administering a Linux environment should feel quite comfortable administering a Linux server as well. And we think that's why we've found quite an affinity with the HPC market. HPC system administrators and users are normally quite familiar with Linux, and when they get a hold of ThinLink and install it and use it and configure it, they feel quite familiar with the product because it is built on these principles. So for example, text-based configuration files and the directory structures that we use mirror Linux directory structures as well. Administration of a ThinLink server can be done either using a web-based administration interface or at the command line. We have support for session shadowing for administrative users, so that an administrator can actually shadow a user's session, and that means controlling the keyboard and mouse and seeing their screen in order to provide end user support. We provide persistent sessions, or otherwise known as hot desking, so that people can close their session in one location and pick it up on another device at a different location, and everything will be exactly as they left it. We do have touch gesture support on those devices that support it, so pinch to zoom and scroll and things like that. And our general principle is that we want ThinLink to work on any device anywhere, so that people have access to their desktops and applications wherever they are from whatever device they happen to be sitting in front of. So where does that place us with regards to HPC? Well, over the past several years, we've actually found a lot of demand from the HPC sector, and that was somewhat unexpected. As a company, we always assumed that HPC users accessed their resources via the command line, that they were all huge Linux geeks, and they had no use for a desktop whatsoever, but we've found that's not actually the case. HPC organizations these days are looking to provide easy access to their HPC resources, especially for non-technical users. They want to expand their user base, they want to increase usage of their systems and make those resources easily available to the widest range of people possible. And one good way to do that is to provide them with a familiar environment, not to provide them with a command line where they just submit jobs and wait for a response, but to provide them with a desktop environment. And because ThinLink has a Linux focus, that makes it a natural fit for this sector and a natural fit for this application. And this is why we're here sponsoring Carla 2020 today, is because we want to promote ourselves in this sector, and we want to gain feedback from people using ThinLink in an HPC application so that we can learn how to make our product better for HPC users. So, as part of this, we are organizing frequent webinars via Zoom. They're not all with an HPC focus, but some of them are. The past 3 webinars that we've had have all had an HPC focus, and they've been really, really successful. These are not marketing events. They are by and for our users. They are designed to allow some of our users to showcase their solutions, which are based on ThinLink, to share ideas with other ThinLink users or others who do not yet use ThinLink, and to basically create a community of like-minded users. These have been very successful in the past, and we've had people from all over the world attending. We've had some really interesting presentations, and you're welcome to join. I'd like to extend the invitation to everybody here today. It is by invitation only. So if you are interested in attending one of these webinars, please get in touch at the contact details I'll leave at the end of this presentation. If you're interested in testing and evaluating ThinLink, it's free and unrestricted for up to 5 concurrent users. That's the full product. There is no restrictions put in place besides the number of concurrent users that connect to the system at the same time. So it is the full product. It's easy and quick to download. If you visit sendio.com, you will see a link there which will allow you to download the server and client packages. It's easy to set up and configure for testing if you just want to set up a small instance just for proof of concept. And of course, if you need any help during this process, just let us know. We'll be more than happy to provide you with support from our team. I personally will be happy to support you through this process. That's my job. So if you do need any assistance with that, just feel free to get in touch. If you do need to get in touch, you can send an email to contact@sendio.com or visit our website, where you'll find more details about the product and also the company. There are links to mailing lists on the website if you'd like to subscribe to them and get announcements about new releases that we make or new features, or join the discussion. Yeah, so I hope to see you there. Thanks for listening, and enjoy the rest of your conference.
Thank you very much for the Sendio partner. Sendio is one of the platinum sponsors for this conference. So now let me introduce you Esteban Meneses. Esteban Menezes is the chair of the poster session, and he has some important information for the people that wants to meet the different rooms. Esteban?
Thank you, Carlos. Just a short announcement. So right now we have the poster session, and you can see on the screen the different posters that we have, and also the links to the Zoom meetings where you can interact with the authors of the poster. Okay. Also on the chat, there is the link to the posters webpage on the Carla 2020 website. So feel free to join the poster session and ask questions to the authors. Thank you.
Okay, thank you, Esteban. So now we left for the different rooms. Please visit the different rooms for the poster sessions and vote for the best poster that do you think about. So thank you very much.